Welcome, this is Information Service Engineering and this is Lecture 3, Linked Data Engineering. In this part of the lecture we want to investigate how to get towards a universal data representation on the web to represent semantics and semantic meaning. So the goal that we have is we want to achieve a web of data. The web of data already exists and we want to understand how it really works. For that, we first have to take a look at the traditional web. Let's have a look at the basic architecture of the traditional web. Everything in the web usually is addressed with the help of a so-called uniform resource identifier. This is kind of an address. So the URL, the uniform resource locator, this is the address of every single web page that you access. How do you get this into your browser? Usually your computer is using a specific protocol with which this URL is requested. And the name of the protocol in the web is the so-called HTTP protocol. This is the Hypertext Transfer Protocol. So URL together with HTTP form an addressing and access mechanism on the web. Now the information that you receive from the web usually is encoded into a specific format. And this format usually is HTML, the hypertext markup language. So, to sum up again, for identification and addressing you use URLs. So for example here http //fitzkarlsruhe.de, this is the address of Fitz Karlsruhe. Then you see in the next line the communication protocol that is used, the HTTP protocol, and which host has been accessed via this HTTP protocol with the so-called GET operation, which tries to get the index page of exactly that host. And then at number 3 you see an example of the representation language HTML, where I have the sentence Mary works at Fitz Karlsruhe, and Fitz Karlsruhe is linked to the web address of Fitz Karlsruhe. Okay, now let's have a look at the web of linked data. What you see here is a huge network of interconnected datasets. They are all available on the web. Many of them are publicly available. Now the question only is, where does the link come from? So how links one dataset to another dataset? And of course, what do these links mean? So what are they meaning? And to make sense of it and to see how this really works, we will have a look at the so-called Semantic Web. The Semantic Web is kind of an initiative that exists now for almost 20 years, and this was planned as an extension of the current web, in which information is given a well-defined meaning with the purpose to better enabling computers and people to work in cooperation. And this kind of initiative goes back to Tim Berners-Lee, who also was the inventor of the web, and other people, other researchers from this research area. And we will see what was the proposed architecture for that kind of semantic web, where information is delivered with a specific formal representation explicitly of its meaning. The technology that is used there is here represented in this so-called semantic web technology stack, which has grown over the years, and you will see this picture again and again within the course of this lecture, since we are referring to all of these or many of these technologies now. Okay, so let's start at the bottom, at the fundament of this interesting technology stack. Here you see the basic web platform where the semantic web is built upon. And usually, of course, we have to identify things about which we want to communicate knowledge. Things which are referenced on the web, usually they have a URI, a uniform resource identifier. And in case of the semantic web, the things we are talking about are not only web pages, but it's also addressing, let's say, things, instances, individuals from the real world, as well as, let's say, artificial or imaginary concepts. Everything has to be identified and addressed with the help of a URI, which is built in the same way like a URL. For example, to find information about the dwarf planet Pluto, I need a URL. And the URL where I find information about Pluto is, for example, the Pluto information that is represented within the so-called DBpedia knowledge base. And you see here the reference to the DBpedia knowledge base, which has been derived from the Wikipedia online encyclopedia. And their knowledge about the dwarf planet Pluto is gathered, is represented, and can be accessed. So this is a typical example of a URI. We will talk about that later. So the URI is one of the building blocks of the semantic web as well as of the web. Next, of course, the access mechanism. All information that will be transferred via the web, of course, will be transferred via the standard protocol that is available on the web. Which means if I want to get information about planet Pluto from a specific knowledge base, I don't use any other dedicated or proprietary protocol. I use HTTP. And I also use the standard web port 80 that is used via HTTP. So this is the standard web mechanism to access information, and this is also used within the semantic web as well as in the web of linked data. Instead of HTML, then, of course, another kind of protocol, another kind of language is used to represent the information that is there. Usually all kind of information on the semantic web is encoded in form of so-called RDF triples. RDF is the resource description framework. And the information encoded in RDF usually is given in terms of RDF triples. Each triple consists of a subject, a property, and an object. So it's constructed like a simple sentence. All sentences in natural language also contain subjects, contain properties, and contain objects. So, for example, if I want to say that Pluto is a dwarf planet, in RDF I could state that Pluto is of type dwarf planet. Whereas we will see that all of this information, Pluto as well as RDF type as well as DBO dwarf planet, these are URLs or URIs referring to some information that is present on the web. So here you see several examples about information of Pluto. But we will dive deeper into RDF in one of the next lectures. So you see RDF is the universal language that is used here to represent knowledge, and together URI, HTTP and RDF, these are the building blocks of the web of data. Of course, they are not sufficient to really represent full-fledged information that is necessary to make sense of the information and to understand the information. What we need there is some means to represent ontologies, knowledge about classes, about relations among classes, about constraints among these relations. We have already seen this in the last part of the lecture. The language that is used here in the semantic web technology stack to represent information or knowledge about classes, about ontologies, is here in the models layer, and usually this is RDFS, which is RDF schema, or the more, or let's say the more expressive language, OWL, which is the web ontology language. Both of these languages we will take care of in the course of this lecture. With this, you will be able to, for example, encode knowledge in the way that you say a planet is a celestial body, or a planet has a discoverer who is a person. So this is possible with the help of RDFS. Moreover, we are able also to create more expressive, more semantically expressive statements. For example, as you have seen here, we can define logical constraints. We have here an example. We say Pluto has the discoverer Clyde Tombaugh. This is the entity level. You remember, assertional knowledge. And we see Clyde Tombaugh is a person, but is also of type dead people. So he already died a long time ago. And we say there is another class which is living people, and we say that the intersection of both classes should be empty, which means these are disjunct classes or disjunctive classes. No individual exists that is likewise at the same time in the class of living people and in the class of dead people. I mean, with the exception of bad movies, for example. And in addition to that, what you can define, for example, based on OWL, on the OWL language, you can, in addition, also state logical rules or add logical rules to your semantic web technology step. You see an example of a logical rule like that, for example, here in the last line. Here this rule says, for all x, and there exists an y, and you say, for all x who have a death date y, and x is a person and y is a date, then x belongs to the class of dead people. So this is a rule which defines who is dead, which means if you have a death date and this is a date and you are a person, then you are among the class of dead people. As simple as that. So this is an example of the other upper layers of the semantic web technology stack. Another interesting technology that is also related to that is, of course, a query language. Because if you define all these things, it's nice, you can build up huge structures. But on the other hand, you also must have means to enable easy and full-fledged access to this information, to analyze that information, to aggregate this information. And for this, you need a query language. And there, of course, exists one, and the name of the query language that is used here is Sparkle. Sparkle works in the same way like the SQL query language for relational databases. No, only here it's a sequential query language which works on an RDF triple store, so which works on RDF. You see here an example of a Sparkle query, and the query here is looking for all celestial bodies that have been named after a Roman or Greek deity. And this information is taken from a knowledge base, which is the DBpedia. We will hear much more about the DBpedia later. And you will always see when we do Sparkle queries like that, I will also present the link to the Sparkle endpoint where this query exactly can be carried out. So if I click on that link, and I will do this here, we will come to the Sparkle endpoint, and you see here exactly our query. And if I click here on Run Query, what happens is that this query is performed on the database, and you see here several subjects, which means celestial bodies, which are named after Roman or Greek deities, to which belongs, for example, Pluto or 51 Nemausa. That's interesting, so I don't know that guy, named after somebody who was named Nemausus. This must be some Roman deity, I guess. Or here we have 1862 Apollo, I guess some asteroid named after the Roman god Apollo, and so on. So you have here several examples of that. Okay, another knowledge base that we will make use of in the course of that lecture besides DBpedia is Wikidata. Wikidata is like Wikipedia, Wikimedia project, which means this is a knowledge base where people are able to complement and to upgrade the knowledge in a manual way. And of course there the knowledge is organized in a different way, but nevertheless it's accessible via Sparkle. And this is exactly the same Sparkle query that you have seen for DBpedia on the previous page, now for Wikidata. And let's now perform exactly that query also on the referring Sparkle endpoint. So you see this here. And the nice thing about Wikidata is that you have some means to visualize the results of your query. And here I have chosen a visualization which is a timeline. And as you see here in Wikidata, there are, interestingly, much more celestial bodies which have been named after some Roman or Greek deity. And the other thing you see here in the timeline is also the date of their discovery. So these are two examples of Sparkle queries. And of course, in the course of this lecture, we will also talk about Sparkle, and you will learn about Sparkle and how to use this, because this is one of the basic technologies that is used for information extraction and knowledge management, also in the course of the ISE lecture. Then in the next part of the lecture, we start in the fundament of the Semantic Web technology stack, and you will learn how to identify and to access linked data based on URIs and HTTP.